What do you see now? Is this the same picture? Do you see anything new in it? What has happened here? Your neural network of a famous physicist contains the name and image of Albert Einstein. By triggering this network, your perception was focused on Einstein's face, and most of you did not notice the pool and the ladies taking a bath. Most of you probably saw Einstein's nose and cheeks instead, because this fits into the neural network of a famous physicist. It's only after looking at the picture of Venus that most of you also notice the ladies taking a bath. This is just a tiny example of how our pre-existing knowledge and our expectations guide our perception. We see what we want to see, or rather, what our neural networks allow us to see. Why do we need to know this, and how can this help? Learning means adding new information or new connections to existing networks. By first calling up existing knowledge, we can help our learners add new bits at the right place. For this reason, we want to always start a new topic by giving a general overview and then adding new details. Good old advanced organizers or pre-reading or pre-listening activities do exactly this. The well-known KWL grid used in most American classrooms does exactly this. K here stands for what I know already. Learners activate their prior knowledge. They search their neural networks for information about the topic. These networks will then be actively guiding what comes next. W stands for what I want to find out. Learners search their brains for possible questions, possible connections, and missing links that will guide their perception during the lesson. And L stands for what I have learned, and requires the learners to actively recap and reflect on their newly acquired knowledge or skills. This will activate the same networks again and thus strengthen them through meaningful repetition and use. The magic of neurons that fire together, wire together, is actually quite simple, but it is so powerful for learning. Let's try this out. Let's apply this new idea in a classroom setting and ask ourselves, why do we not remember word lists or vocabulary lists, as well as vocabulary learned in real-life contexts or multi-sensory contexts? Can you explain this phenomenon? Why do we not remember word lists as well as vocabulary learned in real-life contexts? Obviously, our neural networks play an important role here. When we learn new vocabulary as single words without any context, in the back of a lesson as a list, as it is the case here, for example, with these two vocab words, the words used to and hilarious, without any context here, we cannot tie them to our existing networks easily. Such new words will have very few connections or links and can therefore not be retrieved easily. Imagine them as disorganized, floating vocab cards. How will you find the one you need? Let's look at the two vocab words again, used to and hilarious. My daughter Anna used to play with her doll Fritzi for hours on end. She used to feed him carrots and to share all her foods with him. We used to go camping in Greece. And the word hilarious reminds me of the hilarious jokes that the Snagglegrollop used to tell. If we can tag new words to existing networks in our brains, we can remember and use them more easily. Our prior networks will add depth and meaning, colorful connotations, images and experiences to the new words, and thus make them part of a wide network in our brain. We will find them whenever we activate the respective network. Single words, on the other hand, will be like needles in a haystack. They may be in there somewhere, but how can we find them? Where do they belong? How do we use them? So let's keep in mind, we always want to tie new information to existing networks. Let's zoom in even further. What we can see here is a basic explanation of signal transmission in neural networks. The schematic drawing on the left shows how chemical and electric signals are passed on from one synaptic ending to another across the synaptic cleft. Neurons consist of a cell body. Information always comes in through the dendrites, the little branches on the left, and is passed on through the axons. In our example, the axon has a strong myelin sheath marked in yellow. This protein insulation allows the signal to jump from one node to the next, and thus makes signal transmission faster and more reliable. The signal then exits through the axon terminal and is passed on to the dendrites of a neighboring cell. We won't go into detail here, this is for biologists and neuroscientists, but we need to understand that this process can be influenced from outside. Teaching is the art of changing the brain. Let's look at this in more detail. One of the most interesting and helpful books on learning and the brain is James Zoll's The Art of Changing the Brain. He tells us that learning is biology, not psychology. And teachers can actually influence this down to the cellular, the chemical level of signal transmission between synapses. It's a fascinating book, very readable for teachers. We want to take a brief look at what teachers can do to help or hinder learning. What kind of tasks and methods are most efficient so learning takes place right in our classroom, right in our lesson? The first thing we need to do is to find the key to the learner's brains. Body, mind, and soul are interconnected. We need to know that emotions are the key to the brain. Depending on the kind of input we receive, our limbic system, that is the emotional center of our brain, will lock up or open the door to higher order processing. Let's look at this door opening function in more detail. The importance of our learners' emotional mechanisms is often underestimated. Actually, emotional and social aspects of learning are at least as important as the intellectual and cognitive ones. Children decide quickly and unconsciously whether to turn their brains on or whether to stay in standby mode. Within seconds, their brain's emotional center, that is the limbic system, will decide whether the teacher's words, voice, and body language match and are therefore authentic and reliable, whether the topic is relevant and interesting, and whether the situation in the classroom is relaxed or threatening. Let's follow the brain along the typical steps from input to learning. A stimulus, in this case, let's assume it's sound waves. The teacher's voice, for example, enters the brain and reaches the thalamus. The thalamus is an important part of our limbic system, our emotional center. Here we have two options. The thalamus filters incoming information, and if the incoming signal is marked as irrelevant, it will be discarded. In our picture, it goes into the bin. This is an important filter. We do not want to worry about all kinds of background noise, cars passing by, and other irrelevant signals in our environment. If the stimulus is perceived as important, or at least potentially important, the thalamus will let it through and pass it on to the amygdala. In our picture, we see two of these yellow almond-shaped objects. Here, incoming signals are checked for their emotional content. Is the incoming stimulus associated with danger, or does it seem harmless? Some of these danger signals are innate. We're born with them. Humans and many animals are afraid of fire, even if we have not yet been burned. Other dangers need to be learned and acquired in the course of our lives. Whenever an incoming stimulus is marked as dangerous, the amygdala sends signals to the hypothalamus and the brainstem, and our body prepares for flight or fight. Adrenaline and other neurotransmitters are released, our blood pressure and pulse frequency rise, our muscle tonus rises, and our body prepares for fight or for flight reflexes. In this case, any kinds of higher order thinking are turned off. This cycle could save lives in the wild, but does it help in exams? I like to call this the triple A reaction, the amygdala, adrenaline, anxiety. It produces a cognitive style that facilitates basic automatic routines, but prevents free associations and any kinds of higher order thinking. Let's go back to the incoming signal and assume that the amygdala has decided it's harmless. Only then is the stimulus passed on to the hippocampus and the cortex. And only then will any higher order processing take place in the cortex. What does this mean? Fear and anxiety prevent learning. We must create a relaxed, safe atmosphere to open our learners' brains. This is really important for speaking activities. Here, danger may not only come from a teacher who penalizes every little mistake. Danger might also come from classmates who laugh at you or find fault at your presentation. In all these cases, no or hardly any learning will happen. Let's sum this up again. Higher order processing and learning will happen if and only if the incoming message is not associated with danger and if it is perceived as important, relevant, and meaningful.